Okay, we are going in this set of problems to use green theorem to solve problem. What it say green theorem? First of all, in this set of problem, we are using vector fields that contains only y components and j components. So the k component will disappear. Second observation, we are going to use the fact that f of x, fx, depend on x and y, but it doesn't depend on z. So the curl of f will be, we know how to calculate the curl of f. In this case, the curl of f will be partial derivative respect to the x, partial derivative respect to the y, partial derivative respect to the z, fx that depend on x and y, fy that depend on x and y, and fc that is 0. And what will be the curl of f, the tendency to rotate? It will be I, it will be I, and now the I component will be 0. Why? Because the I component involves the derivative respect to the y of 0, this is 0, and the partial derivative respect to c of f of y, but f of y depend only on x and I and y. So the partial derivative of respect to z is 0. So the I component is 0, the j component is 0, and the only component that survives in this problem is the k component. So it will be k multiplied by the partial derivative respect to the x of f of x. F of x is the x component of the vector field. It's not the derivative. It's the x component. Of f of y. F of y. The partial derivative respect to the x of f of y minus the partial derivative respect to the y of f of x. And that's all in this case. So the curl, the tendency to rotate, is done by the curl. And now let's go to say what it say green theorem. Green theorem relates the line integral over a closed curve C of the vector field F scalar ddr, the line integral of the vector field over a closed path is related with a double integral. Of what? Of what? Is a double integral of the partial rest of the y component respect to the x minus the partial of the x component respect to the y ddx ddy. So what we have here? What we have here is the k component of the curve. So we could write here, instead of this, the curve of f k components. We could write, instead of this, we can write the curve of f, the k components, But we leave it like this to do the problems. So now is something very, very important to understand. In the same way that the first fundamental theorem of calculus relates a region to the information in a region to the information of the region is contained as the difference between 2 points, the antiderivative of the functions evaluate at the 2 extreme points. In the same way, the information related in the boundary is related with the information inside the boundary. The area, ddx, ddy, the area. So, for example, there are some tools that you draw a line like this, very, very strange lines, and they can say what is the area here. This type of tools is being used for people who are measuring areas of the land, for example. And these kind of tools are using the green theorem. So the green theorem appeared in the years 1800s, and it appeared for the first time in my electricity book. So let's go to use it to play with this. Let's go to do a proof, a intuitive proof of this theorem. When you have a curve and you do the line integral of the vector field in the counterclockwise direction, so as you are moving, your left hand is pointing to the interior. The left hand is pointing to the interior of the regions. So when you are calculating the line integral, you are calculating the line integral over the boundary of the regions. Now imagine that you divide the region into many small regions. So let's go to divide the region into many small regions like this, like this, like this, like this, like this. So in each region, you say there is a tendency to rotate of the vector field. There is a tendency to rotate of the vector field. There is a tendency to rotate of the vector field. There is a tendency to rotate, so you think about line integrals, and you think about the curve, the tendency to rotate. And the curve of the vector field is the limit when the area S sub I tends to 0 of the line integral of the vector field f ddr divided by the small area S sub I. So in every small square like this, we subdivide many times. In every small square of this, we think about the line integral going like this, the line integral per unit of area. Wow. So the line integral per unit of area is here. Multiplied by the area is the line integral. And the sum of all this line integral, what it is? The sum of all the line integral, you see here the line integral, when you do this counterclockwise and you do this line integral counterclockwise, on this intersection, the line integral that you are doing in this small piece of a square is in the contrary direction as the line integral that is doing in this. Let's go to right to put it here, so you have two pieces. So the line integral that you are doing in one piece and the line integral that you are doing in the other piece, let's go to put it red, and red. So here, in the boundary, they cancel the line integral. In the boundary, they will cancel with the one that is here. And the line integral, so I will perform the line integral like this, and the counterclockwise direction, and it will be 0 in this. The line integral that is here, it will be cancelled by the line integral of the elements that is in the boundary. So when I do the line integral in the counterclockwise direction, now the line integral in the counterclockwise direction will cancel here. You see? So there are many cancellations. What is the total cancellation that we have? Everything except the boundary. So the line integral of the vector field over the curve C is exactly the line integral per unit of area. This term multiplied by the area makes the summation. And you will have the line integral over the boundary, over the curve C. This explains a little bit why this can be truth. Okay, let's go to use this theorem to make sure that we understand what we are doing. The problem say to verify, it doesn't say to prove. It does say that verify Green's theorem in the case of a vector field where f of x is y squared, f of y is x squared. And it say the curve C is lying between the graph y equal x and y equal square root of x. So let's go to erase here everything and we start. So let's go to start. So here the line integral that they say us to work is the line integral f scalar ddr or fx ddx plus f of y ddy. Then we can recognize that f of x is y squared, so depend on x and y. F of y is x squared, so depend on x and y. In this case, depend only on x for f of y. And what our Green theorem say, it say when you do the line integral over a closed path, if f is conservative, the line integral over a closed path is 0. But in this case, this vector field, the vector field f equal fx y squared I plus x squared j, this vector field depends on x and y, but is not conservative. Otherwise, the line integral will be 0. So, what the problem say? The problem say, find the line integral over the curve C. Which curve C? The curve C is the boundary of the region line between the graph y equal x and y equal square root of x. So find this line integral and check that this is the double integral over the region R contained in the curve C of the partial derivative of f sub y respect to the x minus the partial derivative of f sub x respect to the y ddx ddy. So we have to check this. Let's go to do it. Let's go to do the right part, the right side of the equation. Let's go to find what will be this part. And later on we will find a number. Let's go to check that the number that we will find here is the same number if we do the line integral of this vector field over the boundary of these two curves. Okay, this is the easiest part. Let's go to start with the easiest part. So this will be the double integral of the partial derivative of f sub y respect to the x. So this is 2x minus the partial derivative of the x component of the vector field respect to the y. This is 2y. ddx ddy. Okay, so what is the region R of integration? The problem say that there are two curves, y equal x, y equal square root of x. So let's go to this integral for what region? The region is y equal x, y equal square root of x. That does something like this. Let's go to do it a little bit more. This point is the point x equal 1. This is the point x equal 0. This is the curve y equal x. And this one is the curve y equal square root of x. And we have to do a double integral over the region that is here. So we will do in vertical stripes. In vertical stripe, we will divide the figure in a stripe like this, and we move the stripe to cover the whole elements. So let's go to do it. So this integral will be the double integral over this region R. This is the region R. This region is the region R, or 2x minus 2y. Now, because I'm going to use vertical stripe, I will put it in the other dy ddx. Perfect. So let's go to do the first integral. What we erase here the r. So let's go to do the first integral, and later on we'll do the other integral. The first integral, the one that is inside the brackets, it would be 2x minus 2y dy, and y will vary from y1 equal x, y1 equal x, to y2 equal square root of x, to y2 equal square root of x, y2 equal square root of x. So what would be this integral? It would be 2xy minus 2, the integral of 2x, that is a constant dy, is the integral of dy, which is y. The integral of 2y dy is 2y squared divided by 2, which is y squared, minus y squared. And this is evaluated between y equal x and y equal square root of x. When is y equal square root of x is 2x square root of x minus y squared is x, square root of x, minus the evaluation of the function as this at y equal x. It will be 2x squared, y equal x, 2x squared minus x squared. And 2x squared minus x squared is x squared. So this will be 2x square root of x minus x squared. And now I have done the integral in brackets. And now I have to do the integral for ddx when x vary from 0 to 1. Okay, so let's go to do it. So it will be the integral from x equals 0 to x equals 1 of 2x square root of x minus x squared dx. And what will be this integral? This is x raised to the power 1, and x raised to the power 1/2 is the square root of x. So this will be x to the power 3/2, 2 times the integral of x 3/2 is x 5/2, divided by 5/2, divided by 5/2, multiply here by 2. Minus the integral of x will be x squared divided by 2, minus the integral of x squared will be x cubed divided by 3. And this is evaluated between x equals 0 and x equals 1. When x equals 0 gives nothing, so it will be 4/5, 1, minus 1/2, minus 1/3. So this will be, doing slowly, 4/5, I write it like 8/10, multiplied by 2 numerator, multiplied by 2 the denominator, multiplied by 5 the numerator and the denominator by 5, 1/2 is 5/10. So I would subtract this, it would be 3/10 minus 1/3. Now I will multiply by 3 the first, it would be 9/30, and I multiply by 10 the numerator and 10 the denominator, it will be 10 divided by 30. So the final result will be 9/30 minus 10/30, which is minus 1/30. Okay, so now we have done the first part, that is that this is minus 1/30. And now what we have to do is the line integral over the path in the counterclockwise direction, pointing the left hand of the guy who's moving through the boundaries, through the curves, to the inside of the region. Always, if you imagine that you are moving on the path of the curve, this is the curve, you are moving. So let's go to do now the line integral. This is another job, and we need to find, remember, minus 1/30. Okay, let's go to do it. I'm going to do it in this side, so I have the information here. So the line integral that I need to do is the line integral over the closed curve. What is the vector field? The vector field is y squared ddx plus x squared ddy. The vector field is y squared I plus x squared j. And the line integral is f scalar ddr, which goes and gives us this expression. Now we need to do the line integral over the closed curve. So we need to move first through the line from x equals 0 to 1 of this rectilinear line. And later on we need to come back to the 0 through the line y equals square root of x. So let's go to do it parametrizing the two curves. So let's go to parameterize first the rectilinear lines. So the rectilinear line is y equals x. So I can parameterize the line by saying that r of t always will be x of t I plus y of t j. So if I choose x of t to be t, ti plus tj, and I leave the parameter t to change between 0 and 1, I have covered the rectilinear line, the portion of the rectilinear line. For example, when t equals 1/2, 1/2 I plus 1/2 j, I'm here, 1/2, x is 1/2, y is 1/2. I have performed. Now, I need to perform I need to parameterize the curves y equals square root of x, but I need to go from the point here, going back to the origin. So I need to parameterize r of t. The good parameterization that I can find is to say that r of t, because t is going to change between 1, let's go to find between 1 and what. So I need to be x of t 2 minus t. So 2 minus t I will give, when t equal 1, will give the point 2 minus 1 is 1, 1i. And the parameterization for the y, because y equals square root of x, so the parameterization will be plus the y of t, but y is a square root of x, and x of t I have write it like 2 minus t, so it's a square root of 2 minus t j. And now I can find the parameterization cessation for a square root of t that is coming back from this point to the origin. So, for example, and t will vary, now will vary from t, will vary from 1 to 2. When t equal 2, this is 0, this is 0, so I'm coming back to the origin. When t equal 3/2, this, I'm here. The x will be 2 minus 3/2, that is 1/2. The x will be 1/2, and the y will be a square root of 1/2. So 2 minus 1/2 is a square root of when t is 3/2 is between 1 and 2, 3/2, 2 minus 3/2 is 1/2, so the x will be 1/2, and the y will be a square root of 2 minus 3/2, 2 minus 3/2 is 1/2, so it will be a square root of 1 divided by 2. Perfect, so this is the parameterization is not unique, but the line integral will be the same one. So let's go to use this information to do the line integral. So the line integral that we have to do is the line integral over the curve C1, that is the rectilinear line, plus the line integral over the curve C2, that is the y equals square root of x that we have parameterized. So what is the y over C1? The y is the t. Y squared is t squared. What is d dx? Well, the x is t, so the d dx is d dt. Plus x squared. What is the x? The x is t, so it's t squared plus d dy. The y is t, so the d dy is d dt. Plus, let's go to do the same thing over the curve C2. So the parameterization over this d dt, now the t will vary from t equals 0 to t equal 1. Now the curve C2, the square root of x, it will vary from t equal 1 to t equal 2. Well, what is the x of t? The x of t is what is the y of t? It's a square root of 2 minus t. So y squared will be 2 minus t. Will be a square root of 2 minus t squared. So it's 2 minus t v dx. But the x is 2 minus t. So the d dx is minus d dt. Minus d dt, minus d dt. Perfect. Perfect. Plus the integral from t equal 1 to t equal 2 of, so I did the y squared, this is this, by d dt, and now I have to do the x squared d dy. The x is 2 minus t, so it will be 2 minus t squared by d dy. The y, I need to do it. The y of t is a square root of 2 minus t, which is 2 minus t 1/2. So the d dy is 1/2, 2 minus t 1/2 minus 1 is minus 1/2 by the derivative, the derivative of the function, it is minus ddt, minus 1 by ddt. So the dy that I have to put here, to write here, I wrote x squared 2 minus t squared, and now I have to write the ddt, that is 1/2, is good, is hard work, 1/2 2 minus t minus 1/2 by ddt, and there is a minus sign here. Okay, let's go to do all this integral, and this should be the same result that we found in the previous, when we do the right side of the Green's theorem. So this will be t cubed divided by 3. T cubed divided by 3, I'm washing here, between 1 and 0 is 1/3, and 1/3 is 2/3. 2/3. Now, 2 minus t, minus ddt, minus. 2 minus t, the integral is 2t. 2t minus t squared divided by 2. And this should be evaluated between 1 and 2. Plus, now this integral. 2 minus t squared multiplied by 2 minus t squared minus 1/2 is 2 minus t 3/2. So it will be, 1/2, 2 minus t, 3/2, 3/2 plus 1 is 5/2, divided by 5/2 is 2/5. And these have to be evaluated between 1 and 2. And now is the final proof. And here there is a minus sign, so this minus sign, I should put it here. So here is a minus sign. Wow. This will be how much? Minus 1 divided by 30. You remember. Minus 1 divided by 30. This will be minus 1 divided by 30. Oh, I hope I will not make any mistake. Let's go to do it. 2/3 minus, when t is equal to, is 4, minus 4 squared, 2 squared is 4, divided by 2 is 4 minus 2. And 4 minus 2 is 2. 2, and now I evaluate the function at t equal 1. Is 2 multiplied by 1 is 2. 2 minus 1 squared divided by 2 is 2 minus 1/2 is 3/2. So I have evaluated this part. Now these 2 will cancel with this 2 and will stay minus 1/5. I'm lucky if I get it. Minus 1/5 of what? When minus 1/5, the 2 will cancel, okay. Minus 1/5, I did the integral here or not? Yes, I did the integral. So when t equal 2 will cancel. When t equal 1 is 1. 2 minus 1 is 1. 1 5/2 is 1. So it's minus 1/5 by 1. So it will be 2/3 minus 2 minus 3/2 is the same that 4/2 minus 3/2, which is 1/2. Minus 1/5. Let's go to pray. Let's go to pray now. 2/3 minus 1/2 is the same that I multiply by 2 and we'll have 4/6. And I multiply by 3 and we have 3/6 minus 1/5. So 4/6 minus 3/6 is 1/6 minus 1/5. So I multiply by 30 and we have 30 divided by 6 by 30. Oh, sorry. I multiply 1/6 minus 1/5 will be 5 minus 6 divided by 6 multiplied by 5. Got it. Done. It's minus 130. So I have checked that it's true that the Green theorem holds. For this case, we need to trust that it will hold for any case. Let's go to the next problem. So what we have learned in the previous problem is that it's hard to do the line integral. So what Gauss say, what Green theorem say, is don't do the left side of the integral, do the right side, do a double integral. So this is what we are going to do. Use Green theorem to evaluate this line integral. F of x, the component x of the vector field is y minus x. The component y of the vector field is 2x minus y. And what it say, the Green theorem is don't do the line integral over the closed curve. Do this over the region R. And what? Do the partial derivative of f sub y respect to the x minus the partial derivative of the component x of the vector field respect to the y. Do these things and be happy. So let's go to do these things so we can find the line integral. What is the partial derivative respect to the x of the component y of the vector field? Well, respect to the x, the partial derivative of f sub y respect to the x is 2. So it's 2 is the double integral of 2 minus the partial derivative of the component x of the vector field, which is y minus x, respect to the y. This is 1, this is 0, minus 1. ddx, ddy. Oh, the problem is solved. So this is the integral over the region R of 1 by ddx, ddy. Oh, and what is the region R? The region R is between the semicircle of radius 5 and the semicircle of radius 3. So what is the area that is between the two of them? So I have the semicircle of radius 5, and I have the semicircle of radius 3. So this is the region of integration. And what is the area that is here? Well, the area that is total area, including this, is pi by 5 squared. If I take the area here, in this area, I take pi multiplied by 3 squared, pi r squared is the area, so I reduce the area, so I have the area that I'm looking in the region that is pi 5 squared minus pi 3 squared. But wait a moment, this is the semicircle. The total area is pi r squared. So I'm considering this upper semicircle, so I need to divide by 2. So it will be, so the integral, it will be the area. And the area will be pi divided by 2, 5 squared minus 3 squared. Or in other words, pi divided by 2 25 minus 9 is 16. 16 divided by 2 is 8. So the result will be 8 pi. Wow. So what we have done, we have used Green theorems to perform a line integral that could be difficult to perform. What we have done is, in an easy way, to relate the line integral, the information of the vector field through the contours, through the boundary, with what is inside the boundary, with the information inside of the boundary. So this is 8 pi. Let's go to the next problem. The next problem says use Green theorem to evaluate the line integral of the vector field whose components, f of x, the x component of the vector field is y minus x. And the y component of the vector field is 2x minus y. And the curve C is the ellipse. So the curve C is an ellipse, and the ellipse have a semi-axis when theta equals 0, is cosine of theta is 1, so the x is 2. So the ellipse will do like this. When theta equals 0, x is 2, and when theta equals 0, the y is 0. So it will start here. When theta equal pi divided by 2, the x is 0 and the y is 1. And when theta is pi, the cosine of pi will be minus 1, so this will be minus 2, and the x will be 0. And when theta equals 3 pi divided by 2, the x will be 0, and the y will be sine of 3 pi we divide by 2, which is minus 1. And this will perform ellipse. And the region is this region, the region inside. So we have to perform the line integral in this direction. And what we say is, don't do the line integral. Apply Green theorem. So a Green theorem say that this line integral f scalar ddr, this line integral fx ddx plus fy ddy, this line integral is the double integral over the region R of the partial derivative respect to x of f of y minus the partial derivative respect to the y of f of x by ddx dy. ddx dy. So it's equal. What is the partial derivative of the y components of the vector field respect to the x? I see a 2. 2 minus. Now, what is the partial derivative, the x component respect to the y? Respect to the y is 1. 2 minus 1. ddx dy. And what is that? 2 minus 1 is 1. So it's the integral of ddx dy. And what is the integral of ddx dy? In the region R is the area of the ellipse. And what is the area of the ellipse? Is p pi by a by b. And what is a? A is 2, b is 1. Oh, pi by 2 by 1. So 2 pi. 2 pi is the line integral. Wow, powerful. So we have now a new problems to apply. So let's go to apply. What is the component x of the vector field? The component x of the vector field is e to the x cosine of 2y. What is the y component of the vector field? is minus 2 times e to the x sine of 2y. What is the partial derivative of xy respect to the x? The partial derivative of xy respect to the x is minus 2 times e to the x sine of 2y. What is the partial derivative of f sub x respect to the y? Well, the derivative of cosine of 2y is minus sine of 2y. So it will be e to the x multiplied by sine of 2y multiplied by 2. So now I can apply the green theory. The green theory say don't do the line integral over the closed curve C. Don't do this. Do the double integral over the region of integration. The region of integration is the circle of radius 3. Of what? Of the partial derivative of y respect to the x. Minus 2 times e to the x sine of 2y. Minus the partial derivative of f sub x respect to the y. Minus minus plus. Plus 2 times e to the x sine of 2y. Wow. ddx, ddy. So here there is a cancellation. Oh, so this is 0. So the double integral of the function 0 over the region, this is 0. Oh, but what it say this? What it say this is that this vector field is conservative. And the problem is done. So we need to do this problem again. And it's the same idea. The idea is, don't do the line integral. Do the right side of the green theorem. That is related with a double integral over the region R. So the f of x is x multiplied by y. The f of y is x plus y. The partial derivative of f sub x respect to the x is y. The partial derivative of f sub y respect to the partial derivative of f sub y respect to the x is 1. And the partial derivative of f sub x respect to the y is x. And now we say this line integral xy ddx plus x plus y ddy. This line integral is equivalent to do the double integral over the region R, and the region R is the unit circle of radius 1 of the partial derivative of f sub y respect to the x, 1, minus the partial derivative of f sub x, the component x of the field, respect to the y, x, multiply by ddx, ddy. And we need to do this integration over the circle of radius 1. So we need to do the line integral over the double integral over this region. So, because this is a circle, we use polar coordinates. So the x is the r cosine of theta. And the y is r sine of theta. But we will not need to use the y, because the ddx by ddy is the element of area. And the element of area in polar coordinates is r ddr dd theta. So when we see the x, we write r cosine of theta. When we see d dx, d dy, we write r d dr d d theta. So the integral over the region, the circle of radius 1, of 1 minus x minus r cosine of theta, d dx, d dy, r d dr d d theta. And now the limit of integration will be when r vary from 0 to 1 and when the theta vary from 0 to 2 pi. So we will have from r equals 0 to r equals 1 of the integral 1 minus r cosine of theta r d dr. And later on we will do the integral over theta. So this will be r squared divided by 2 minus r squared, r by r is r squared, the integral is r cubed divided by 3 by cosine of theta. And this is evaluated between r equals 0 and r equals 1. R equals 0 gives nothing. So this will be 1/2 minus 1/3 cosine of theta. Now I need to do the other integral, the integral over theta of 1/2 minus 1/3 cosine of theta d d theta from theta equals 0 to theta equals 2 pi. And then I will have covered the whole region. So it will be 1/2 by theta minus 1/3. The integral of cosine of theta is sine of theta. Sine of theta is the function whose derivative is cosine of theta. And I need to evaluate this integral between 0 and 2 pi. When I put 0, this is 0, this is 0. So for 0, give nothing. For 2 pi, we'll give here, we'll give pi minus 1/3 of sine of 2 pi, which is 0. So final result is pi, and the problem is done. So now, same idea. Let's go to work. The idea. The component x of the force is x 3/2 minus 3y. The component y of the force is 6x plus 5 times square root of y. The partial derivative of a sub x respect to the y is minus 3. And the partial derivative of the y component of the field respect to the x is 6. And the Green theorem say that f scalar ddr over a closed curve C is equivalent to do the double integral over the region R contained in the curve C of the partial derivative of f sub y respect to the x minus the partial derivative of f sub x respect to the y ddx ddy. So we have solved the problem very easy. The region of integration is moving in around a triangle with vertices. It's moving around the triangle. So let's go to C. So the partial derivative respect to the y is 6. Minus 3 is plus 3. 6 plus 3 ddx ddy is 9. So it will be 9 times the integral of ddx ddy. So it will be 9 times the area of the region contained in the curve C. But it said that is a triangle. So this is 0, 0, this is 5, 0, and 0, 5, 0, 5 is here. So this triangle. This triangle, this is the triangle, and the area of this triangle, this is 5, this is 5, let me write 5, and this is 5, the area is 1/2 base by the height, 25, divided by 2. 1/2 base by the area, so 25 divided by 2, so it's 9 times 25 divided by 2. And the problem is solved.